Okay, so now why do we want to remove this junk? Well, the reason it's important to remove this junk is because it prevents quantum interference. So let's see an example of this. So suppose that we had a circuit that on input X just outputs X. So X is a bit and the circuit just does nothing to it. It outputs X as is. So of course, if this was a quantum circuit and we input summation alpha x x, then the output is also summation alpha x x, because it does nothing to the input. Okay, so now suppose that we have this quantum circuit, and then further we feed the output into a Hadamard gate. Okay, and let's say that we set up the input to this circuit to be in the plus state. So let's say the input was 1 over square root 2 0 plus 1 over square root 2 1, and now so the output of the first circuit is also the plus state, and when this is fed into the Hadamard, out pops the 0 state. So if we were to measure this output, we'll see 0 with probability 1. Okay, so this is what we wanted to happen. Okay, but now instead, let's say we started with this classical circuit, which on input X outputs X. So this was our classical circuit. We convert this into a reversible circuit. So R sub C, and let's say that the process of converting it into a reversible circuit, the following happens to it. So it takes as input X as well as some clean bit 0, and it outputs the correct answer, but it also creates some junk. And let's say the junk it creates is a function of X, and in fact it's X itself. So it just makes another copy of this input bit. Okay, now since this is a reversible circuit, all the gates are reversible, we go ahead and make this out of quantum gates. Maybe our universal family, maybe using just the C swap as including C swap in our universal family. So now it takes as input 2 qubits, outputs 2 qubits, where now what we'd like is to understand what happens when we feed the output into a Hadamard gate. Right? So we take as input the plus state 1 over square root 2 0 plus 1 over square root 2 1. And this clean bit. And now the output of this circuit is 1 over square root 2 0 0 plus 1 over square root 2 0 1. And now what happens when we actually do a Hadamard of the first qubit? Well, this part goes to 1 over 2 0 0 plus 1 over 2 1 0, and this gets transformed to 1 over 2 0 1 plus 1 over 2 1 1. So we get all 4 strings. And now what happens is when we measure the first qubit, we see 0 and 1 with equal probability, which is different from what we had here. So let's see what happened here. Well, you see, what happened here is that when we did our Hadamard transform on this first qubit, so let's say we do a Hadamard transform here. Okay, so So let's see first what happened when we did the Hadamard here without the junk qubits. Well, so 1 over square root 2 0 after the Hadamard went to 1 over 2 0 plus 1 over 2 1. Whereas 1 over square root 2 1 after the Hadamard went to 1 over 2 0 minus 1 over 2 1. And so when you start with the superposition of these two, you have to add these two, and this part cancels, so that's destructive interference. This part reinforces each other in constructive interference, and you get as outcome half plus a half, which is 1 times 0. What happens here? Well, here, this piece gets mapped to that, and this piece gets mapped to that. But see, before, in this case, this minus should have cancelled that one. And so you should have been left only with the first qubit equal to 0. But now the second qubit doesn't allow these two pieces to interfere with each other, because these two are different states. These are orthogonal states. They can't interfere with each other. And so the presence of this junk here, junk of x, actually prevents an interference pattern from happening. And so we get the wrong results in our quantum computation. Okay, so you can still ask, well, can't we just throw away the junk qubits? The answer is no. You can't throw away the junk qubits. You see, because remember what, you know, we had our state when we fed in 1 over square root 2 0 plus 1 over square root 2 1 and a 0 here. What we got out was 1 over square root 2 0 0 plus 1 over square root 2 1 1, which you might recognize as the Bell state. So now in the Bell state, if we throw away one of the qubits, right, throw it away, you know, send it to the other part of the city, send it across the country, doesn't matter, they're still entangled, right? You can't just throw it away. You can't change the state of these two qubits to a tensor product state just by throwing away the qubit. In fact, when you throw away the qubit, it's as though you measured it. Okay? So this really doesn't help at all. What we have to do is somehow make sure, change the circuit so that the junk qubits are not created. It turns out there's a very elegant way of doing this. So what do? Well, let's remember this was our reversible circuit. It takes as input x, a bunch of zeros. It outputs c of x, the correct answer. But then it also outputs this junk, which may be a function of x. So what are we going to do? Well, remember it's a reversible circuit, so we could apply the reverse of the circuit. Okay, so we have the inverse of this circuit, and if we apply it, it gets rid of the junk and restores all these bits back to 0. But of course, there's a problem, because it also takes the answer c of x and it restores it to x. So that's not very good. It's, you know, we've thrown out the baby with the bathwater. So how can we get rid of the junk but also keep the answer bits around? Well, the answer is simple. All we do is copy it. So what we do is before we apply the inverse circuit, we just start with some fresh bits where we set y to be all zeros, and then we do a C0 from each of these answer bits into these y bits. Okay, so if y is 0, then we get a copy of the answer bits, the output of the circuit. And now we are free to run the inverse of this circuit. And so what it does is it erases the junk, erases the answer, restores the input. And so what we have finally is what we were looking for. We have a circuit where we gave as input X, a bunch of zeros, maybe Y is also zeros. And what do we get as output? We get a bunch of zeros, we get X. So the input is copied over. This is important for the reversibility. And then we get the actual output we are looking for. Okay. And now the point is that there's no junk. There's no junk associated with the input. And so this circuit, if you now write as a quantum circuit, it actually does what we want, and it doesn't prevent interference. Okay, so what's the upshot of what I've been saying so far? The upshot is, if you are given any classical circuit, if you give me any classical circuit C, which takes as input X, it outputs C of X. What I can do is transform this into a quantum circuit. Let's call it U sub C, which takes as input X and a whole bunch of zeros. And what it does is it outputs X, C of X, and zeros. Okay. Now, because this is a quantum circuit, you could also give it as input a superposition sum over X, alpha X, X. And in the second register, we have a bunch of zeros. Now, what's the output when you apply this circuit to it? You get superposition over X, alpha X, X in this first register, C of X in the second register, and a bunch of zeros in the third register. Right? You remember the notation that we had, right? So the notation was, if you write down X, Y, this is the same thing as writing X tensor Y, and we even can write it as X, Y. It's all the same. It's just notation for saying you have this many qubits, these are in the state X, these are in the state Y. It's a tensor product. Okay, but this is our basic theorem. It says, given any classical circuit, you can convert it into a quantum circuit. Okay. It turns out that, okay, so historically, the initial interest in quantum computation started not with trying to show that quantum computers could be much more powerful than classical computers. It actually started with people who wondered, could it be that quantum mechanics imposes further constraints on what can and cannot be computed? So could it be that this fact that quantum mechanics is unitary and so reversible, does this mean that not everything that you can compute classically is allowed by quantum mechanics? So maybe there are some constraints that we weren't aware of so far. And of course, this shows that there are no such constraints, and it shows that given any classical circuit, you can actually make a corresponding quantum circuit. Okay, and this will turn out to be a very useful primitive as we move forward into quantum algorithms.